NASA's Voyager 1, the farthest human-made object in the universe, is once again sending useful data to Earth after months of transmitting confusing signals. Even with decades of exploration, our solar system continues to surprise scientists with groundbreaking discoveries. For years, we thought we had a clear understanding of the planets and space beyond. Yet, the Voyager probes have shown us how little we truly know. One of the most fascinating findings is that our entire solar system, including the distant Oort cloud about a light-year from the Sun, is encased within a giant bubble. This bubble spans 1,000 light-years, with the Sun sitting near its center. But what happened when the Voyager spacecraft crossed the boundary of this solar system bubble? Could we truly be living inside a massive space bubble? And how does this discovery reshape our understanding of the solar system? Let's explore. Voyager 1 was launched on September 5, 1977, just weeks after its twin, Voyager 2, on August 20. Both probes were originally designed for a 5-year mission to study the outer planets. However, they far exceeded expectations, continuing to send data back to Earth over 44 years later as they venture into interstellar space. These missions were made possible by a rare planetary alignment that happens once every 107 years, allowing the probes to use gravitational slingshots to conserve fuel. Voyager 1, launched second but traveling faster, reached Jupiter and Saturn first, while Voyager 2 went on to explore Uranus and Neptune, becoming the only spacecraft to visit these planets. Both probes carry golden records with Earth sounds and music, intended as messages to any potential extraterrestrial life. As of January 2024, Voyager 1 is about 14.9 billion miles from Earth, making it the most distant human-made object in space. Voyager 1 entered interstellar space in August 2012, followed by Voyager 2 in November 2018. When Voyager 1 crossed the edge of the solar system's protective bubble, called the heliosphere, it detected a stark difference in conditions. The heliosphere is formed by the solar wind, a stream of charged particles from the Sun, which creates a boundary as it meets the interstellar medium, the remnant of ancient stellar explosions. The outer edge of the heliosphere, known as the heliopause, marks the transition into interstellar space. Voyager 1 confirmed its crossing when it detected a solar eruption that caused surrounding electrons to vibrate. The data revealed that interstellar space is denser than regions near the Sun, while the heliosphere's outer edge is much less dense. Voyager 2 provided additional insights with its functional plasma instrument, which Voyager 1 lost in 1980. It observed that plasma near the heliopause became slower, hotter, and denser, offering a clearer view of the dynamics at this critical boundary. These findings also revealed surprising details about the interstellar medium. It is far hotter than expected, with temperatures exceeding 54,000 degrees Fahrenheit, though the extremely thin plasma keeps the average temperature around the probes low. Voyager 2 confirmed that the heliopause is porous, allowing particles to pass between interstellar space and the heliosphere. Voyager 1, for instance, detected streams of interstellar particles penetrating this boundary, resembling tree roots breaking through rock. Interestingly, Voyager 1 and Voyager 2 observed differences as they crossed the heliopause. Voyager 1 experienced a slowing solar wind near the boundary, while Voyager 2 detected a transitional layer in the solar wind, highlighting the complex nature of the heliosphere. These observations suggest that the heliosphere could be shaped like a sphere, a comet, or even something more irregular, but its exact structure remains unknown. Unfortunately, the Voyager probes won't last forever. Voyager 1 and Voyager 2 are expected to lose power in the 2030s, and other spacecraft, like NASA's New Horizons, will run out of energy long before reaching the heliopause. For now, the Voyagers remain humanity's best tools for exploring the mysteries of the solar system's edge, revealing a dynamic and protective cosmic bubble that shields life on Earth from the galaxy's harshest radiation. The limitations of the Voyager missions have led to growing interest in launching a follow-up interstellar mission. Exploring the farthest reaches of the solar system and beyond requires more data, as the information we currently have comes from only 2 points. To truly understand the structure of the heliosphere, additional observations are essential. Voyager 1 also made an intriguing discovery outside the heliopause, a persistent hum. Upon entering interstellar space, its plasma wave instrument detected oscillations in interstellar gas caused by solar activity. Between these events, however, the instrument picked up a faint and continuous low-frequency signal. This monotonous but steady hum hints at more subtle activity in the interstellar medium than previously understood. Monitoring it helped scientists map the distribution of plasma in interstellar space, allowing them to study how the interstellar medium interacts with the sun's solar wind, a constant stream of charged particles flowing from our star. While the Voyager missions have provided priceless data about the solar system and interstellar space, they also underline how much remains unexplored in the vast unknown beyond our solar system. In the past, studying interstellar plasma relied on random solar events, but Voyager 1 and 2 have changed that, giving us a treasure trove of data collected over decades. Their discoveries have illuminated the immense power of cosmic radiation and the interactions between solar and stellar particles, expanding our understanding of space. Voyager 2's reanalyzed data has even unveiled new insights into Uranus. Nearly 40 years ago, during Voyager 2's historic flyby of the planet in 1986, scientists captured groundbreaking data, such as the discovery of new moons and rings. However, observations of Uranus's magnetosphere, its protective magnetic bubble, were puzzling. The magnetosphere appeared strangely empty of plasma, leading researchers to believe Uranus was fundamentally different from other planets in this regard. Recent studies have shown that this anomaly was caused by a rare solar wind event that compressed the magnetosphere and pushed plasma out. These events are extremely uncommon, occurring only about 4% of the time. If Voyager 2 had arrived at Uranus just a few days earlier or later, the conditions observed would have been completely different. This updated analysis has also changed our understanding of Uranus's moons. Scientists once thought that the lack of plasma meant the moons were geologically inactive. However, it's now believed that the 5 largest moons may be geologically active and could even host subsurface oceans or other dynamic features. The solar wind event may also explain why Uranus's radiation belts are unusually intense, second only to Jupiter's in strength. This discovery emphasizes the importance of timing during planetary flybys and highlights the need for dedicated, long-term missions to planets like Uranus. NASA's planetary science goals have even prioritized a mission to Uranus to study its atmosphere, magnetosphere, and moons over an extended period. Meanwhile, Voyager 1 recently demonstrated the resilience of its design. In October 2024, the spacecraft experienced a communications issue when its primary transmitter unexpectedly stopped sending data. Engineers detected a faint signal using a backup transmitter which had been dormant since 1981. This backup transmitter, while functional, operates at lower power and provides less detailed data. Its activation likely resulted from Voyager 1's fault protection system, designed to ensure the spacecraft's longevity. Detecting this weak signal posed a challenge because of Voyager 1's immense distance, over 15 billion miles from Earth. NASA's Deep Space Network successfully captured the faint signal, verifying the spacecraft's operational status. However, the backup system cannot relay detailed telemetry, limiting the team's ability to assess the spacecraft's condition fully. NASA engineers are carefully exploring the possibility of reactivating the primary transmitter to resume detailed data transmissions. This event highlights the ingenuity behind Voyager's design, which included redundancies for critical systems to ensure mission success over the long term. Troubleshooting such issues in deep space is no small task, especially when commands take nearly 2 days to travel between Earth and the spacecraft. Looking ahead, the Voyagers will continue traveling through interstellar space long after their power sources are exhausted. In 1 billion years, these probes will be far from our solar system, drifting silently through the galaxy. Voyager 1 is heading toward a distant star called AC plus 793888, and Voyager 2 is on a path toward Ross 248 in the Andromeda constellation. Though these stars will only come near the probes in tens of thousands of years, the Voyager's journey symbolize humanity's enduring curiosity and drive to explore the unknown. As they continue to drift, the Voyagers will carry with them not just scientific instruments, but also humanity's message to the cosmos, the golden records. In the years to come, new discoveries and breakthroughs inspired by the Voyager's data are likely. If history has taught us anything, it's that the most exciting revelations may be those we haven't even imagined yet.